Welcome to lecture 33. We are going to talk about using regression to make predictions today. And as always, we'll start with a few announcements. This is an unusual week because we have a Thursday holiday, which we don't normally have. And so since homeworks are normally due on Thursdays, we've pushed that back to Friday. And tomorrow, being a holiday, Thursday's labs will not be held, but the Thursday's lab GSIs have posted alternate times today or Friday morning before lecture. So if you can make those, please go to those. Office hours will be held 12 to 5 as usual in 145 Moffat. If you need help with your lab, please go. And then every student will get credit for labs if you can by passing all the tests by noon on Friday. And there is extensive, all the details are on the Ed post here. So let me just see, Will, are there any questions that we need to answer?
No, I think
we're good.
the students are asking. Yeah, well, the students are asking about extra credit, and you can submit by Thursday to get extra credit.
All right. So let's just have a recap of where we are. Thus far, we have been looking at the relationship between two numerical variables drawn on a scatter diagram as usual. And what we did was, in the cases where that scatter diagram looked linear, we felt like we should be able to identify what is the line that is going through that scatter diagram that we can somehow see in our heads, but it's not actually drawn there. And so we defined something called the regression line, which, as you saw last time, is in the sense of the least amount of squared error, the best straight line that you can fit through any data set. Now, the scatter diagram may be straight, it may be curved. Regardless, there is exactly one best straight line that goes through that scatter diagram. You might not want to use it if your scatter diagram is curved, but there is a best among all straight lines, and it has the equation that you know, and last time you also saw how to find it by numerical minimization. So up to that point, what we had been doing was just describing the data that we have. But really, one of the most significant reasons for doing these kinds of analysis is to make a prediction for the next point that comes along, for which you know the value of X, but you have not yet measured Y. Right? So you haven't measured the variable, the response, that is the variable in which you are interested. So today we're going to see how to do that and what assumptions we will make about the nature of the uncertainty, and then how to understand that uncertainty. And that will end our discussion on regression. On Friday, we'll move to the last phase of the course, where we will talk about a particular method that is used a lot in machine learning, and Professor Wagner will introduce that with a lecture on privacy. It's not a heavily technical lecture, but it is one of, I think, one of the most important lectures of the class, so please do show up. All right, so I'll do a quick recap of how to assess whether your regression is any good. And of course, you can look at correlation and so on, but last time you saw that looking at the residuals, the errors, is a very good idea. So let's just take a look. What is a residual? It is the error in the regression estimate. And so for each point on the scatter diagram, you have a corresponding point on the regression line that is your estimate, and now you're off from that. Residual comes from the word residue, what's left over after you've done your prediction. So it is the actual Y minus the regression estimate of Y. And so it is your observed Y, that is the height of the actual point, and then minus the height of the regression line, and that's a vertical distance. And you saw last time that if you draw a scatter diagram of the residuals against the X variable, the variable that you are using as your in order to predict, If your regression is good, this diagram should look like a blob, no pattern at all. If you have nonlinear scatter diagram, then that nonlinearity will show itself very clearly on the residual plot. So you should use always, when you do a regression, you should do a residual plot to check whether your linear regression was actually a good thing to do. What you're looking for is any kind of pattern, curves, changes in spread, yes. However, you can still have linearity even though you have scatter diagrams that are narrow in places and wide in places. Outliers have a big effect on correlation and therefore on your regression line and therefore on the quality of your regression. So today I want to start with a few facts about residuals that at least one of which should be very easy to understand intuitively. These are errors. So sometimes the errors are positive. That's when your point is above the line, so you've underestimated. And sometimes the errors are negative. That is when the point is below the line, and so you have overestimated. And what happens is if you look at the average of the errors, what do you think you're going to get? Got a bunch of plus errors, you got a bunch of minus errors. Yeah, you've seen that with deviations from average. You're going to get zero mean. Always, 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 no matter what the shape of the scatter diagram, no matter how bad your regression is, the residuals will have zero mean. It turns out, and this can be shown, though we are not going to show it in this class, that they are not correlated with X. And this has a certain visual aspect to your residual plot, which I'll talk about. So they're not correlated with X, they're not correlated with the fitted values. What are the fitted values? Those are your predicted values of Y. If you had a scatter diagram, where would you see these fitted values, these predicted values of Y, on what kind of graph, what kind of curve? Your predicted values are where? On the line of best fit. Very good. So the predicted values are always on exactly a straight line, right? The actual values are off a little bit. Okay, and so these facts are true no matter what the data. And so let's take a look in a notebook. Okay, so this is the notebook that you have. Run your import cell, and now I actually want to go over all of these functions that were defined over the last few lectures. So standard units takes an array and returns the array converted to standard units. The correlation function takes a table, the X and Y columns, and returns the correlation between X and Y by following the formula. You convert both to standard units, take the product, and then take the average. The slope function has the same three arguments and returns the slope of the regression line for predicting Y based on X. So this is the one you're given. The first argument is the one you're given, and the second is the one you're trying to predict. Intercept, same thing, but it returns the intercept. And then you have two more functions that return arrays. One is called fitted values. And what this does, it regresses your Y. It finds the regression predictions of Y based on X. And for every X in your data set, it returns the prediction. So it returns an array of predictions. And residuals returns the corresponding errors. And please note in what way the residuals are defined. It is the actual Y minus the predictions. Okay, quickly, questions about this sequence. Each one is pretty straightforward, and they all use the previous ones. Okay, so all of these were defined last time. I'm just going to run them. So you should note somewhere that we now have a whole bunch of functions that we can use to calculate slopes, correlations, and so on. Okay, so I'm going to remind you of a data set we had last time about this lovely animal called the dugong. And the goal here is to use the length to as a predictor of the age, partly because it is much easier to measure the length of a dugong than to ask it what its birthday was to find out when, to find out how old it is. So that was partly the reason for this. And our scatter diagram showed a positive correlation. I mean, 0.82 is significant, but it's quite a large correlation, 0.83, but there's a clear curve. Nevertheless, if you fit a straight line, by the way, you know that if you draw a scatter diagram, then you take your table, scatter, horizontal axis, vertical axis, those are the arguments. If you add the argument fit underscore line, fit line equals true, then lo and behold, on the scatter diagram, you have the regression line. Okay, so, I mean, it kind of follows the scatter diagram, but you can see the points are above the line on the left and on the right, but then they are below for most of the other parts, and that is suggesting that we have a curve. And so what we have done is, to this table, we have augmented, we have added two columns. One is the predicted age for each of these 27 dugongs. So there'll be a column of predictions here. And then once we have the column of predictions, we have also done the residuals. And what we're going to do now is we are going to draw the residual plot. That is the plot of the residual on the y-axis and the given value on the x-axis. So there's always this question about the sign of the residual. If the residual is positive, that means the actual value was bigger than your predicted value. And so your predicted value was an underestimate. Okay, look at that residual plot. Okay, you can see that some of the residuals are above zero and many of them are below zero. What we learned from our result is that if you average all these residuals, you'll get what? You will get zero. So let's do that. Okay, if I take the average of the residuals, well, I got this tiny little number. Why don't I just round the thing? I'll round it to 6 decimal places and see what I get. I get a nice 0. Okay, so the average of the residuals is 0. The minus deviations exactly cancel out all the positive ones. And we also said that the correlation between the residuals and x is 0. That means, from a visual perspective, your residual plot, you should expect it to be in general flat, right? It may have patterns, but it will not have a trend. You will not see a correlation that is going up, or an association that is going up or going down. So what we're going to do is we're going to compute the correlation of the length, which is our x variable, and the residual. We're just going to compute it. And well, that looks very zero-ish. And the point for you to note is that if you have done your regression correctly, and if you have calculated your residuals correctly, this will be the case in every single scatter diagram, every single regression that you do. The residual plot cannot show a trend. The residual plot is going to be flat. It can show a pattern, however. Here we have kind of a U, and that's telling you don't use a straight line, please. All right, so now what we're going to do is we are going to look at the predicted age versus the length. Can somebody tell me that scatter diagram is going to look like what? If I plot the predicted values versus the x, it's going to look like a straight line. It better look like a straight line. Okay, terrific. So if you look at the length and you look at the predicted ages, these are basically just a change of units of measurement, one from another. Okay, it's just, it's linear, and therefore no surprise if you draw the residuals versus not the length, but the predicted age, you get exactly the same plot as you got when you had length here. I'm just going to scroll up and show you. So here's one plot, and here's the other plot. You have length here. It's precisely the same plot. You just have different numbers. And so what is the correlation going to be here? Residuals versus predicted age. You should get exactly the same as you got with the length, which was 0, and this better be 0. Okay, so these are things to keep in mind when you draw a residual plot. And so let me ask you to just check. Supposing you used a line to make a prediction, right? And you calculate, well, actually, this should not say residual. It should say if the errors on average were 10, then what should we do? What have we learned about our line? If on average your errors are 10, yeah, your line, the line is not the best fit. Exactly, this is not the regression line. Yeah, it's too low, right? So it's not the regression line. So how about we go back and use the regression line? That would be a good way to adjust. What if the residuals were positively correlated with your given variable? So these, again, this should say errors rather than residuals. If somebody tells you that I've had I've done a regression and I've got residuals and they're positively correlated with my X. There you go. You did something wrong. That is the conclusion. This is mathematically impossible. The regression is not done correctly. If somebody tells you they did a regression and their residuals came out to have some kind of positive or negative trend, then their regression was wrong. Right? It could be wrong in, so either the regression was wrong or their subtraction was wrong or something. There's an error in their calculation. And you can't tell exactly what the error was. Okay, what is the difference between error and residual? That's a very good question. We use the term error when we're using a line that is not any arbitrary line. Residual is very much tied to the regression line. Positive correlation is not a pattern, it's so much, it's a trend. All right, and a trend in a residual plot is flat out impossible. It's not that the regression is bad, it's that the regression is wrong, that you actually made a calculation error. Okay, now, if the residuals were above 0 in the middle and below 0 on the left and right, then what should you do? Change the slope, explore nonlinear regression. Exactly, because you're seeing a pattern now, right? Your line is a little too low in some places and too high in other places. And so you should use a nonlinear curve. So what is the difference between a pattern and a trend? That's a very good question. I'm going to show you. Okay, take a look at this. All right, this thing has correlation 0, but there's a clear pattern. There's a U-shaped pattern. So the graph is largely flat, but you can see that there's a curve in it. So you have a pattern. A trend is a graph that in general slopes upwards or in general slopes downwards. Trend is a direction. Does that help? Right. Okay, so now what we're going to do is we're going to move beyond describing the data set that we have and try to use our data to make a prediction for a new individual. And so here, here we are going to look at what we mean by a linear relation, right? So if you have two variables like midterm score and final score, there is no universe in which the final exam score is actually a perfect linear function of the midterm score. Yet, if you draw a scatter diagram, maybe you see a somewhat linear relationship. And so where is that line? Well, the line's in our head. It is an assumption that we're making about what we see. And so we're going to spend a little while trying to make that assumption a little bit more precise and to say, where is randomness? Here's a question about, so we will never see a trend in the residuals unless we did something wrong. That is a true statement. But we could see a pattern which could indicate that we shouldn't be using linear regression. That is also a true statement. That is beautiful. Yes, exactly. If you can cut and paste that, copy paste that, and next time, Thomas, you're going to give the lecture. Okay, so let's take a look at a model. A model, as you know, is a set of assumptions. Okay, so here is the model. This green line is this linear relation that we are imagining between X and Y. And what we're saying is, okay, there is a line there, but we don't actually see the line. The points are on the line, except that somebody has gone and shoved them off the line by some error. And the regression model assumes that that error is drawn from a normal distribution with mean zero. So sometimes it's positive, sometimes it's negative, symmetrically on either side. And it assumes that for different points, the errors are drawn independently of each other. And so there's a lot of mind games going on here. We are imagining that somewhere, somebody, the all-knowing people, have some linear relation between our two variables, but they're annoying. They won't show us that linear relation. They will show us that linear relation, but jittered by some noise. And we make these assumptions about the noise. And if we do that, then what do we see? We see these points, but we don't see the line. And therefore, we don't see the red errors either. This is what we see. And what we are trying to do is to try and see, well, where was that green line? So we have to take our best shot at where was that green line given these points. What do you think we are going to do? What do you think we're going to use as our estimate of that true green line? You got a bunch of points. Yeah, you're going to find the best line that you can put through these points, and that is the regression line. So let's see what happens when we do that. And so now, by the way, this lecture has a lot of visual demos, and you don't have to worry about the code for any of that. Here's what I am going to do. Let me explain what I'm going to do here. I'm going to first run the code. Okay. So this is a picture where we have drawn a line that has slope 2 and intercept -5. And we have drawn 10 points using the regression model. So we drew the line, and then we drew 10 independent normal errors with mean 0 and the same SD. And then we added that to various points on our line, and we got these 10 points. Okay, so this is what the model says is happening, except our reality is that we don't get to see this. We get to see this. And this now starts to resemble the kinds of scatter diagrams that you've been seeing, right? It's just a bunch of points. Our goal is to try to understand where this green line was. We are never going to be able to see the green line. What's the best that we can do with these points that we have? The best that we can do is draw the regression line. So that's what we do, right? We say we think the green line is here, right? But is the green line actually here? Well, in this case, because we were in touch with the all-knowing individuals, we are going to plot both the green line and this regression line, which is the regression line is the thing that we can compute. Okay, and that comes out like that. You see that they're awfully close. Now, it need not always be this way. So what I'm going to do is I'm just going to run exactly the same code again, and I'll get a different set of 10 points because the errors are always being drawn at random. So here we go. And now we get a different set of 10 points. And now the scatter diagram that we're seeing is different. Look, this one kind of maybe even looks somewhat nonlinear. I'm not sure. Okay. And so we fit our best straight line through it. And we compare that to the true line, and this one's off. So our conclusions are based on the few random points that we see. And therefore, if the random points, just because of chance, don't look very much like the original straight line, then our estimate is going to be off. How do you create the true line? We actually never do. This is an example in which we are pretending that we are starting with creating the true line and actually drawing the scatter plot. But in reality, you will not have the true line. Okay, so these are examples where we are not generating the true line from a normal distribution. The true line is just an ordinary math line. We are generating the errors from a normal distribution because that is what the model says. What I'm going to do is I'm going to run the same thing now, but now with 100 points. We just had 10 points. That's not a lot of data. Okay, so with 100 points, there's your true line. I'm keeping the true line the same. It's still slope 2 and intercept -5. And now we have 100 points. And so this is what we get to see. This looks like a very typical linear scatter diagram. So we put our regression line through it. And wow, it's almost indistinguishable from the green line. It's almost indistinguishable from the true line. What is that telling us? That is telling us that our regression estimate is a pretty good estimate of the green line. So of what we call the true linear relation between the two. It's a pretty good estimate of that. Let's run this again and see how far off we can be. Okay, so here we have another set of 100 points. We put a line through it. And once again, it's pretty close. And so what are you learning from these pictures? That if your data actually come from the regression model, if the regression model makes sense for your data, and you have quite a large amount of data, then your regression line is a pretty good estimate of the true line. All of this can be made mathematically precise, but that's not what we do in this class. This time, we're just going to observe. So I'm going to pause for a second, take questions on what you have seen, and then use this in the context of some real data to make predictions. Okay, while you're thinking about your questions, let's, the true line is the underlying linear relationship, which we think is there. Okay, so yeah, Lawrence, in our particular simulation, we chose a standard deviation. You can choose any standard deviation you want. And okay, so for regression prediction, what are we going to do? If the data come from any regression model, then the true line at X is the true value of the response Y at that X. And so that is the height that we are going to try to predict. So what are we going to do? Well, we don't have the true line. So we're going to use a regression line because we think it's close, especially if we have a lot of data. This should be reasonably, this should be a reasonable conclusion. And so we are going to look at that X and find the point on the regression line and say that is our estimate for where the true line is. And so why don't we just do that? Okay, so this is a familiar data set. What we're going to do is we are going to use gestational days, which is the number of days the mother is pregnant, to predict birth weight. And, you know, these are widely varying. The Centers for Disease Control has some definition of preterm babies and post-term babies. And so, you know, 250 to about 300 is roughly the sort of standard range of gestational days according to the CDC. We looked at all our data, and we are just going to restrict to looking at standard births. And so we are going to restrict to roughly 200 to roughly 300. Okay, and so we have a scatter diagram that looks like that. Now, you do have some points that we have left out. We have left out a few of these points. Those are outliers in this picture, and they deserve to be looked at separately. These points are interesting because babies were born quite early compared to everybody else, but their weights were still roughly average. maybe the doctors had a hand in that. This baby was born a little bit early and was quite small, and these are also a little bit different. But we are going to look at the sort of standard range of days. And so our scatter diagram looks like that. So what do you think? Roughly linear. I mean, not tremendously clustered, but roughly linear. Looks reasonable. And so if we assume the regression model, there's some line going through this, that is the green line. Question to you, are we ever going to know what that green line is? We are never going to know what the green line is. What is the line that we can draw? We can draw the regression line. And so just for some numerical sense of the association, the correlations, 0.42, not great, but not zero either. And if we can draw a regression line, and so our picture looks like that. This black line, this is our regression line. This is our estimate of the green line. Okay, and so now somebody says, okay, I'm going to give you a baby, and I know that the number of gestation days was 300. What is your prediction for the weight of this baby? Well, you will say, well, the weight of this baby is actually the height of the true line at 300. I don't have that. So the best I'm going to do is I'm going to walk up and I'm going to find the height of my line, my regression line at 300. I'm going to make that my prediction. Okay, and so why don't we do that? Okay, so we're going to define a new function, prediction at this x value. And what it takes is the name of the table, the label of the x column and the label of the y column. And then what it does is it returns your prediction. Now, what's your prediction? It's linear. So you take your x, you multiply by the slope of the regression line, and you add the intercept of the regression line. And that is what the function is returning. Quickly, questions about what that function returns? Is it going to return one value or a whole bunch of values? It's good. The way it's different from fitted values, it returns exactly one value. X value is just one number, and so it is going to return one value. And so if we do the prediction for a 300 gestational days, then the prediction at 300 comes out to be 131-ish. And so does that look reasonable? So 300, okay, that right there is 120, that is 130. Yeah, a line somewhere in the middle between 120 and 130. Okay. Okay, so now true or false? This 130.80 is the height of the true line at 300. True or false? False. It is the height of the regression line at 300, and that therefore it is our estimate of the height of the true line. T is the name of the table, X is the label of the X column, and Y is the label of the Y column. Okay. And so here's what we've done. We've stood at 300, we've gone up to the line, and our 131 roughly was here. That's our prediction. Terrific. Okay, so we're done. Except no, because I mean, the errors are random under our model, so our scatter diagram could have come out differently, could it not? If we chose another set of babies and mothers, then you would get a different set of errors. And so this prediction is very much based on this set of points, but the points could have been different. And so we have to account for that. And so what are we going to do? We're going to make another sample. How do we make another sample? We bootstrap. You know this, right? So why don't we just bootstrap the sample and create another sample? But before we do that, is it clear why we are doing that? We want to get some sense of the variability in this regression line if our sample changes. Okay, so how do we bootstrap? Somebody remind me. How do we bootstrap a sample? You sample with replacement how many times? What's n? The same number of times as the original. Yes, exactly. And the code for that is right here, this line. You take your table and you sample, and the default is to sample the same number of times as the original table with replacement. And this code is not something that you need to understand, but you do need to understand that we have bootstrapped the table. And what we are doing is every single time we are drawing you the scatter diagram. So this is your original sample. This is the first bootstrap sample. Can you take a look at those two and see, are they exactly the same? I usually look at extremes. I have these 3 flat points here. I have a whole 4 flat points. They're not exactly the same, but aren't they very similar? Yes, they're very similar. Is that a surprise? Not anymore, because you're master bootstrappers. You know that if you take a sample and you bootstrap it, then the resulting thing looks very much like the original sample, but not exactly. And that not exactly is what gives us the variation. Okay, so you have another bootstrap sample and another bootstrap sample and a whole bunch of them, and they all look kind of similar, but not exactly the same. Now, if this were our sample, isn't there a regression line that goes through this one, bootstrap sample, this first scatter? Yes, there is. Is it going to be exactly the same as the regression line we got before? It is not, because the data are not exactly the same. So is our prediction at 300 going to be the same based on these points as it was based on our previous ones? No, it is not. It's going to be a different prediction. It's going to be similar, but it is not going to be exactly the same. But can we make the prediction? You bet we can. We will bootstrap the table, and we will do exactly the same thing to the bootstrap table that we did to the original table. We will draw the regression line and we will make our prediction. So that's what we've done. And okay, so we have a bunch of bootstrap samples. Here's a bootstrap sample, and our prediction was 131 and a bit. Here's a second bootstrap sample, and the prediction was also 131-ish. Okay, and the predictions are all slightly different. The lines are all slightly different, and the predictions are all slightly different. Okay, and so I'll put all of the lines in the same place for you. Because if I put all the scatters on the same scatter diagram, you won't be able to see anything. It's going to be a great big mess. But at least we can try to look at all the different lines. All right, so here we did this 10 times. We got 10 bootstrapped samples. And in each, so we had 10 regression lines, one for each sample. And in each case, we had a prediction at x equals 300. And you see that the predictions are close, but not exactly the same. Okay. So we have these 10 lines. I want you to notice something. They're all kind of intersecting somewhere. They're all kind of meeting up kind of here, aren't they? You see that? They're all pretty close. Okay, what do you think that point is? All of these regression lines are going to go through their points of averages for their own scatter diagrams, and those are all going to be very much like the point of average of the original scatter diagram. So the original sample had a mean of 279 on the x-axis and a mean of 119 on the y-axis. So you can see that is why they're really close, just about here. Okay. And now somebody's already asked the question. We did 10 bootstraps here and we got 10 estimates. How many bootstraps should we do? How many do you want to do? We can do a whole bunch, right? We can do as many as we have the patience for. Let me just, before we do that, let's just take a look at, if we did 10, then we would get 10 different samples, hence 10 different slopes, 10 different intercepts. And we made a bunch of predictions at 291, at 300, and at 309. And we got a bunch of lines. And what we've done is we've just drawn for you the zoomed in to x equals 300. And you can see that these are all rather different. And of course, now you want to do it over and over again. And so let's just quickly summarize what we're about to do. We're going to bootstrap the scatter diagram. You're going to get the prediction using the regression line through your bootstrapped scatter diagram. And then we're going to do this many, many, many times. And then we're going to draw the empirical histogram of all of the predictions, and we're going to pick off the middle 95%. Does this seem familiar? You bootstrap your sample, you calculate a statistic, and you draw its distribution and pick off the middle 95%. Yes, it's a confidence interval. It's a confidence interval for what? First, it is that range is a set of predictions that we're making. We're saying that, okay, we think the height of the true line at x equals 300 is somewhere in this range. Okay. And so this is a confidence interval for the height of the true line, the green line at x. That is something we're never going to be able to see, but our model says it's there, and we're guessing roughly where that is. Okay, so let's run through this again. So this is a function, a bootstrap prediction. It'll take the name of our table, the label of our x column, the label of our y column, and then it'll take the x where we want to make the prediction. Okay, and so we're making a prediction for somebody who we think is a new individual who looks very much like the old individuals. We just haven't measured their y yet. So we have to decide on the number of repetitions. People have been asking that all through the chat. By default, we are going to take 2,500, but you can put in a number of repetitions, some different number if you want. Okay, so much of this, this bottom part is all display. We will not focus on that, but we will try to understand the beginning of the code. Okay, so we're going to bootstrap the scatter diagram, make a prediction at new x, and collect all the predictions in a collection array. As always, we start with an empty collection array. And then for as many repetitions as we want to do, what does this first line do? Resample equals t dot sample. What does that line do? This line right here. It bootstraps the table T. It does not actually bootstrap the scatter plot yet. It is bootstrapping the table. You're going to get another table. And so we now take that table and we apply our prediction at function, which takes also the new x and returns the prediction for that table. And we attach that prediction we append that prediction to our collection array. Right? So if we do this, we will have, say we do it 2,500 times, then we'll have 2,500 times a bootstrap sample and therefore 2,500 predictions. And then in a very familiar move, the left end of the prediction interval, the right end of the prediction interval, and then I've done some display. And so if I run this, that's the definition of a function. Now, what are we doing here? We are going to take our sample and we are going to try to predict the birth weight of a baby who has 300 gestational days, okay, by bootstrapping our original sample 2,500 times. And I run this and no surprise, it's going to chug for a little bit. While it's chugging, questions? Okay. So this is a 95% confidence interval for the height of the true line. As somebody says here, it's Thomas again. 95% of the times we run this, our confidence interval will include the height of the true line. Yes, that's correct. Okay, so we have our interval. We are saying that for a baby who has 300 gestational days, the weight of the birth weight of that baby, at least the true birth weight on our true line, is somewhere in the range. This is roughly about 129 to 132.5 roughly. That's what we're doing. Okay, so I knew I would come to this point. I'm going to quickly make a point without going through a lot of detail. I'm going to make one point, and then we are going to move on to a more important part, which is that if you, okay, you see, we were making a prediction at 300 and there was some spread. If we had taken a baby whose gestation days was 280, we would get a variety of predictions. Would the spread be the same as for 300 or smaller? Supposing we'd gone here. If this was X, smaller because this is where the lines are all coming together. Right, so the thing to keep in mind is that the variability of your prediction depends on how far your X value is from the average. The closer it is to the average, the more tight your predictions are going to be. The further it is from the average, the more variable your predictions are going to be. You can see that on the graph. And I think we say that on the slides, so I will just say that since X is correlated, Y is correlated with X, your width of the prediction interval depends on X, and the further you are from the center, the wider your intervals are going to be. And there is actually a section in the notebook that just does that a bunch of times, but I am going to skip that because I want to get to a more important question. This is a question that is used, that comes up quite a lot. Okay, so here's our regression. Okay. So what's the slope? 0.53 was the slope here. So 0.53 ounces per day. Okay. Is that the slope of the true line? This 0.53 that we figured out? Is that the slope of the true line? It is not. It is the slope of our regression line. So it is an estimate for the slope of the true line. If we had a slightly different scatter, then we would get a different estimate. And if we had a slightly different scatter yet again, we would get yet another different estimate. So can we bootstrap the slope? You bet we can. We will bootstrap the sample. We will calculate the slope. And then we will do that over and over again. And then we'll have, well, 2,500 slopes. And then we have some sense of how big the slope of our true line is. So this is exactly the same as before, except after bootstrapping, we are not getting a predicted value, we're getting the slope, right? And we are going to collect all the slopes and make a confidence interval for the true slope. So here we go. Confidence interval for the true slope coming up. Dun-da-da. Okay, so what do we think? We think the slope of the true line is somewhere between, what about 0.46 to about 0.62-ish, right? Wonderful. So what? Well, that's the good news. We have some sense of what the true slope is, right? So you bootstrap the scatter diagram, you find the slope from each bootstrap scatter diagram, and then you collect them all, and then you take the middle 95%, right? So you have guessed, this is your guess for what the true slope is. If you run this process 100 times, then about 95 of your intervals will contain the true slope. Okay, except, that's what we just did, except along comes the statistician, right? And so you're all very happy. You got a slope based on your sample of points. And now I start to bother you. But yours is just a sample. What if the true line didn't have this slope? What if your slope was just by chance? And worse still, what if the true line was actually flat? Why is that important? That is important because that means the X is not having any effect. And so I want you to see what the issue is here. And then we will stop. So I'm drawing a line with slope 0. That's the true line. It has slope 0. Here are the points that we get to see. We fit a regression line. Are you seeing a slope here? Yes, absolutely. We're seeing a slope here. The actual line was flat. We see a slope, but this slope is because of noise. It's not the reality. Right? And so we might go away saying, oh, yes, these things are related to each other and so on, but they're actually not related to each other. And so what do you think we are going to do with this confidence interval? If I ask you, is this slope equal to 0? What do you think you're going to do with this confidence interval? Null hypothesis, true slope equals 0. Alternative hypothesis, true slope not equal 0. What are you going to do? There's your confidence interval. It's from 0.46 to 0.616. What are you looking for? You're looking to see whether 0 is in it. Is 0 in there? Absolutely not. It is not in there. And therefore, you're going to say, no, the true slope is not 0. This is something that you've done before. And I'm going to really rapidly run through a regression of birth weight on maternal age. Okay, there it does not look like there's anything going on here, but there's actual, if you calculate the slope, it's 0.09. Well, okay, so there's a line. If I want to test whether the true slope is 0 versus not 0, I'm going to make a confidence interval. Chug, chug, chug. And your interval goes from minus 0.09 to 2.69. Are you seeing 0 in there? You're seeing 0 in there. So these data are consistent with the slope of the true line being equal to 0. All good? Okay, I am going to stop recording now, and I will